So hello everyone, and thank you for coming today for the next installment of Merle's seminar series on this most auspicious day, March the 14th, not because of the rain. It's my pleasure to introduce Dr. Suraj Srinivas, who is a postdoctoral research scholar at Howard University. Suraj finished his PhD from EDF Research Institute and EPFL, Switzerland, in 2021, and his thesis won a distinction award. His work has also won multiple awards at various machine learning workshops. And his main research focus now is interpretability, efficiency, and robust deep learning models. Let's hear from Suraj.
Thanks, Vas, and thanks all of you for making it today, amidst all this rain. I didn't realize I was giving this talk on the auspicious occasion of Pi Day, so that's pretty cool. So today I'll be talking about the pitfalls and opportunities of feature importance methods in post-hoc interpretability. I'll start this talk by talking about this problem, the so-called alignment problem in machine learning, which is really a very old problem that you're all very familiar with. It's this problem that there's often a gap between the intent of the human algorithm designers and the behavior of models in practice, right? So for instance, there's this famous case of machine learning algorithms being biased against certain racial groups or against some genders, or more recently showing behaviors that are not really expected. So for instance, in the image that is generated by Stable Diffusion, we see that the image of a sports game also has the logo of Getty Images, which forms the basis of the lawsuit that Stable Diffusion finds itself under exam. What we call the alignment problem is really a gap between human intent of human algorithm designers and model behavior in practice, right? So the way we actually have to overcome this is that we need to characterize model behavior more comprehensively, right? So for instance, if Stable Diffusion, for instance, had really had the time to look at all the images that it generates, or if Amazon took the time to actually characterize model behavior more comprehensively against all sets of users, then these problems might have been avoided. So most of the time, these alignment problems happen because our machine learning algorithms are trained to pick up correlations rather than causations, right? And when there's a gap between the correlation structure in the data set and the actual the causal structure, that's when we see a misalignment. Right? So for instance, let's say we are interested in classifying cats versus dogs, right? So a human would go back and collect data sets of cats versus dogs, but then they would obviously recognize that the discriminative portions here represent the faces of the cats or the faces of the dogs, right? But for instance, if this data set hasn't been collected well, then it's possible, for instance, for there to be a correlation between the structure that we wish to represent and, for instance, a distractor, here being the background, right? So for instance, if it happens that all cat images are taken indoors and all dog images are taken outdoors, then the classifier can just look at the background to make this classification. Right. So this obviously is a cause of represents a misalignment between human intent of the algorithm designers and the model behavior in practice. So the question is, how do we characterize this difference between these two different worlds without actually having a lot of additional data, right? So this is what trustworthy machine learning and post-hoc interpretability broadly aim to do. And in particular, we look at one particular branch of feature importance of post-hoc interpretability, that is feature importance, that aims to answer the question, what are the most discriminative input regions according to the model, right? So the question is, what do we mean by discriminative regions? So let's look at this image of the dog in a park in a little bit more detail. We can ask whether it was indeed the object that caused the classification by actually changing the object under question. Right, so we could replace the dog with something else, like a horse or any other object, and see the classifier still says that it's a dog, right? Or on the other hand, if you think that it's the background that actually caused the classification, then you could actually change the background and see if the model still identifies the image as a cat, like as a dog, right? So essentially, what we mean when we say that we want to find what the discriminative regions are or what we mean when we say that we want to find out where the model looks at, is done by analyzing response to counterfactual inputs. Right? You can't just look at the model response to one particular input. We need to construct a bunch of counterfactual inputs and use the model behavior there to make any conclusions about what the discriminative regions are. But the problem with using something like generative models, in this case stable diffusion, is that generative models can have spurious correlations of their own, right? So what if the generative model itself learns the spurious correlation between the dog and the background, in which case we will not be able to disentangle this relationship. And further, doing this actually requires us to know the source of spurious correlation a priori. So because we have this hypothesis going into the problem that maybe it's the background or maybe it's the object that enabled us to make this experiment. But on the other hand, errors in real world scenarios might be far more nuanced than this. And in particular, we'd like an exploratory tool that enables us to find out the sources of spurious correlation without actually having a hypothesis a priori. And this is exactly where feature importance tools come in. So they are essentially exploratory tools that we can use to identify sources of spurious correlations. And this image represents, essentially the promise of feature importance tools in this particular example. So in this example, a classifier was trained to, classify between, I guess, husky dogs and ordinary dogs, I guess. And in this case, the explanation that is given by this particular paper, which is also called LIME, actually shows us that it's the background that seems to be the most discriminative in making this classification. So this indicates that it's not even the face of the dog, but the background that the snow, in fact, that it uses to make this decision. And we can use this to diagnose errors in classifiers, right? Right. So this is the promise of feature importance methods as an exploratory tool to identify spurious correlations. And to talk about a little bit more detail about what we mean by feature importance methods, I'll start off with one simple example, that is the input gradient saliency map. So for instance, if I have an input X and a scalar valued neural network F, then I can just take the gradient of the output F with respect to the input X, and that represents how much the classifier is sensitive to small variations in each of the input pixels. And here we can see that, although I don't know how much you can see that in the slides here, but it seems that the head of the dog here indeed seems to be the most sensitive parts, which seems to indicate that all is right with this particular classifier, right? But of course, the problem with using simple methods like gradients is that gradients are zero at local extrema, right? So for instance, if there's an input at a local extrema of the function f, then it's going to have zero gradients, which is not desirable. So a large portion of the work in interpretable machine learning is to essentially overcome these problems with input gradients, essentially. How do you overcome the saturation problem that is basically produce attributions regardless of the geometry of the function, essentially, right? So for the rest of the talk, when I say feature attribution methods, you can think of input gradients as one example, right? So the rest of the talk, I'll do the following. First, we look at what do we actually mean, how do feature importance methods in practice work? How do they actually overcome the saturation problem, for instance? Here I talk about our recent work on a unifying framework for local function approximation, for feature importance via local function approximation. And we'll use this to discuss some of the pitfalls of these methods, right? And in part C, we'll look at why do these feature importance methods work in the first place, despite the existence of all of these pitfalls, right? Where we'll discuss our work in ICLR 2021. And finally, we'll close by discussing how we can avoid these pitfalls, right? Okay. Any clarification questions before we dive into it? Awesome. So we'll start by discussing this particular paper, which explanation should I choose? Function approximation perspective to characterizing post-hoc explanations. And this is joint work with Tessa Han and my postdoc supervisor, Himala Karaju. Okay. So if you look at the landscape of post-hoc explanations or feature importance methods out there, there are actually different philosophies of what people assume explanations are. So for instance, there's this one particular paper on Lime, which assumes that explanations are nothing but function approximations, right? And there are some papers based on Shapley values or integrated gradients, which say that explanations are nothing but approximations of the so-called Shapley values or Shapley-Yeoman cost sharing, which is a notion that comes from economics, right? On the other hand, there are some other methods like smooth grad or even GradCam that say that what is essential for a good explanation is that it produces a good visualization, right? So we see that we haven't come across a single notion of what it means to be an explanation, and people have different notions of what constitutes a good explanation in each of these papers in literature. So there exists a fragmentation of the very fundamental definition that we want to make progress on, right? But then if you go back and ask any physicist, for instance, what do you mean by an explanation? Or any scientist for that matter, they will say that an explanation is basically a simplification of the real world that explains the behavior of the real world in some specific domain. Right? So for instance, like Newtonian mechanics or E equals mc square or quantum mechanics, for instance, there are simplifications of the real world that explain the outcome of certain precise experiments. And for instance, you cannot expect, for instance, quantum mechanics to explain natural selection, for instance, right? So these strictly are valid in different domains. And that is what constitutes understanding or an explanation in the natural sciences. And so the question is, can we kind of use a similar notion of what it means to be an explanation for machine learning models, right? And okay, I'll probably move this so that you can see the figure here a little bit better.
Yeah.
Oh, yes.
In the upper left, just minimize the little box.
Yes. Yeah. So, right. So one notion we can think of for what it means to be an explanation is that it is a local function approximation, right? So in this toy figure here, let's say this orange thing is the complex black box model that we wish to quote unquote explain. The way we could do that is by simplifying the black box model to produce simpler model G, which forms part of an interpretable model class capital G here, and which is centered around the point that we wish to quote unquote explain, which is x0, right? So the idea is that I approximate the complex black box model F to give a simplified model G around a point x0 using perturbations psi, right? So remember that we said that one essential thing that we needed to do to identify what it means for a model to look at any particular place is to actually generate a bunch of counterfactual inputs, right? So this is exactly what the counterfactual inputs actually represent. So for every explanation, there exists a specific domain of input perturbations, which are the counterfactual inputs, and we fit, for instance, a linear model in this case, right? But in the local function approximation kind of perspective, it could be a model that forms as a part of any interpretable model class, not just linear models. Right? But in the LFA framework, we see that many popular post-hoc explanation methods that exist in literature, regardless of the motivation in the original papers themselves, they can all be written in this form. That is, if you look at smooth grad, vanilla gradients, integrated gradients, Lime, Shap, occlusion, and so on. So all of them can be viewed in this manner. That is, there exists a local neighborhood around the input, and there exists a loss function which they're implicitly minimizing. And all of these happen for the case of the interpretable model class being linear. Right? So this is basically the main message of this particular paper, that many explanation methods in literature can be written in this manner. So there are some obvious omissions here, that being GradCam, for instance. So I think many of you might be familiar with this particular method called GradCam. You might ask, where does GradCam fit into this framework? And we'll answer that question a little bit in the next part of the talk. But to answer it briefly here, it doesn't show up in this table because GradCam turns out does not depend on the discriminative model at all. So it's actually a fundamental flaw with GradCam, which is why it does not show up in this table. Right? Okay. And this kind of way of talking about explanation methods helps us state a quote-unquote no free lunch theorem for explanation methods, which basically states that there is no such thing as the best feature attribution methods for arbitrary models. right? So a lot of work in the feature attribution or the interpretability literature is focused around saying that, here I propose a new metric that, beats the previous feature attribution methods and so on. So the implicit goal is to find the quote unquote best feature attribution methods. But here we say that there is no such thing essentially. And the way we kind of square that with intuitively is that in the realm of natural sciences, there's no such thing as, quote unquote, the best theory, and different theories are valid in different domains. You can't expect the theory of quantum mechanics to explain, thermodynamics. Maybe that was a wrong example, but let's say some experiment in biology, for instance. Right? So different theories are valid in different domains. And we also see this happening in practice with explanation methods. So one of the ways in which we can actually test whether an explanation method is good or bad is by using something called the pixel perturbation test, where the idea is that we perturb the bottom k features and test whether the model actually changes its prediction. So for instance, in the example of the dog, for instance, if the feature attribution methods told me that the background is not important, then I can perturb the background and then see the model still classifies it as a dog, right? But then there are different ways in which I could perturb the background. I could either replace the background with zeros, or I could just add some noise to the background. These are like different ways to kind of perturb the background. And these corresponds to either binary perturbations, that is replacing the background with zero, or continuous perturbation, that is adding some noise to the background. And it turns out, and in this curve, essentially lower is better. And it turns out that one class of methods shown in blue here, which all essentially use a neighborhood derived from binary perturbations, do best when tested under binary perturbations, and similarly for continuous perturbations, where the curve exactly reverses. So depending on how you choose to evaluate the goodness of explanation methods, one set of methods come out on top versus another. So basically, this tells us that there's no such thing as the best explanation method. It all depends on how you evaluate your methods, and you can't expect a single method to perform best across all neighborhoods. Right. So the takeaway from this part of the presentation is that LFA provides a conceptual unification of popular post-hoc attribution methods in the literature using local function approximation, and that there's no such thing as the best method in terms of capturing model behavior. But then there's kind of bad news for our overall goal of finding out feature attributions. So what does this mean? That depending on the method, they give us like different outputs about which parts of the inputs are important and which parts are not. And if you'd like to play around with the code, we have it here. But maybe I'll pause here for a little bit to see if there are any questions in the audience.
So when you're approximating with the linear function with these various methods, so I'm trying to square this with the visualization. So the visualization is looking for where the greatest gradient is, the highest value of the gradient.
Yes.
So if it's a linear model and you're at a peak, that's going to give you nothing.
Yes.
But it'll still, I guess if you didn't use a linear model, it would show you where the peak is.
Yeah.
So for these linear models, it just sort of shows you what the best direction is in that case.
Exactly.
And then for the other methods, I guess if it's not a linear model, it'll show you where the max is.
Yeah, so the problem is that all of these actually work on linear models. Although not shown here, it's all of these work on linear models. But the only thing that's different is the neighborhood around which these operate. That's the only difference. And if it turns out that the neighborhood is, for instance, not symmetric around the maximum, then you can hope to get like a non-zero kind of slope. And that's how exactly all of these methods avoid the quote-unquote saturation problem. I'm not saying this is a good thing to do, but this is basically mechanically what they do.
So they'll always push you away from where you are now. It's basically assuming you're never quite at the.
Moitreya has a question. He's attending online.
Hey, so so I just had a quick question about this. So I was curious if semantics sort of plays a role here, because I understand that you want to add the perturbation formulation is a nice mathematical way of doing this, but if the discriminators and all of these are learning semantic features, then isn't the right counterfactual thing to do to introduce something that's sort of more semantics related. So for example, as you showed, like changing the background of the dog class or whatever, like where you kind of have a shift in the semantics rather than, because like I don't know if there is a interpretability issue to this perturbations that you're introducing. Like what changes do they result in the image? So it's just
That's a
curious
very
what
good point, actually. Yeah, that's a very good question. Yeah, that's very true that we'd like, the counterfactuals to be kind of quote unquote meaningful. But I think the main question here is how do we exactly do that, right? So an example that I can provide here is that, let's say there's a classifier that looks only at the ears of the dog, for instance, to make the classification, right? So the counterfactual is something that is basically like, dog ears floating in the air, but then dog ears floating in the air is not a valid image from any generative model that I know, right?
Right.
So how do we square this? It's a very kind of interesting problem in this case. How do we generate valid counterfactual images? But I agree that yeah, that's a very important consideration, which is not taken into account in any of these methods.
All right, thanks.
Right. Okay. Okay, so maybe I'll just move on here to the rest of the talk. Okay, so having seen a little bit about what other feature important methods do, we are in a position to ask the question of what are the pitfalls of all of these feature attribution methods, right? So maybe we'll make this part of the presentation a little bit more interactive. And right, so let's look at this particular example of occlusion, right? And occlusion works in the following manner. So let's say I have a particular image given to me. I have exactly a black box, which has slides throughout the image. And then for every position that the black box is in, I record whether the class prediction changes from the original class that it produced. And here we see that if the black box is exactly at the face of the dog, it produces a misclassification and not otherwise. Right, so this is the canonical occlusion method, which was proposed by Zieler and Fergus, which should have been cited there. But the question that I want to ask you is that, do you see any problems with this method? Like, what problems do you see with this method, essentially?
Maybe because it's looking only at the face, so that's not a good thing.
I mean, so that's the thing to do with the model, right?
Yeah.
So the question is, what's the pitfall of this explanation method? Yeah.
You have to pick the
size of the box.
Yeah.
Exactly. So yeah, we don't know, what's the optimal quote unquote perturbation to use. That's one thing.
Yeah, it's sort of assuming local receptive fields in order to make this decision. I think.
Exactly. Yeah. That's true. Yeah. One other
Also,
thing. Sorry.
there's just one box. There seems to be just one box, right? It doesn't necessarily have to be the case that maybe like, there are multiple discriminative regions and just like.
Yeah, that's a very good point. Exactly. Yes. Right. Yeah, those are actually all very good points. Okay. So one of the problems with this, which I think was also mentioned previously in the question, was that if you remove patches like this, it leads to out of distribution inputs, right? So which is not ideal. Like, we don't know how the classifier is going to behave on these out of distribution inputs. So this need not work at all, right? And the other point that was already raised twice was that this assumes that objects are convex and connected, for instance, right? So what if the image has two dogs? In that case, this method would not work, right? Because even if you occlude one dog, the other dog is still visible and it doesn't work, right? But also, the choice of the gray square itself, right? Where did that come from? And what if it triggers some other class, for instance, like a television or something, right? So this is something that's like, specific to this particular interpretation method, that is occlusion. But then it turns out we can kind of generalize this to all of the other methods that we saw today. And we list that as quote unquote 3 broad pitfalls of feature attribution. The first thing is that we perform feature attributions to black box models, whether or not they may exist. So this is exactly the problem of having, of generating out of distribution counterfactuals, when we know that standard models may have undefined behavior on these counterfactuals, right? So if you look at all of these LFA methods, for instance, all of the 7 popular explanation methods that we looked at, they all rely on generating some kind of counterfactual inputs from some distribution or looking at gradients, but then standard models may have undefined behavior on these regions. Right? And in particular, the behavior of the model on training points and the behavior of the model in the neighborhood are completely independent quantities. And there's no reason one should inform the other. Right? So this is the first pitfall of interpretability of black box models, that it may not even exist, for instance.
Sorry, I don't quite understand either of these points. So undefined behavior on a neighborhood, what do you mean by that? Standard models have undefined behavior on a neighborhood.
So when we train standard models that say minimizing cross entropy error, we only regulate its behavior at the training points, but we do not regulate its behavior at the neighborhood of the training points. So it can have high curvature, low curvature, it can be robust, non-robust, and we don't know what's going on in the local neighborhood. But then we use this exact behavior to interpret these models, which can be a bit of a problem.
I see. Okay. Go ahead.
Also, having the gray box, is that still in the neighborhood in the first place? Or?
It depends on what you mean by the neighborhood. It's just actually just a programmatic way of generating counterfactuals.
But in the slide, the gray box in some part of the image is still part of that neighborhood.
Right. So it exactly means, what do we mean by the neighborhood, right? Here I mean neighborhood in a very kind of broad sense. It's just a programmatic way of generating the counterfactuals here. Yeah.
It makes for odd gradients over those neighborhoods, I guess. If you have
Sorry?
Seems like it makes for an odd gradient.
Yeah.
And what's the other one about the neighborhood behavior and the gradients? You're saying there are two different ways of looking at it.
It just means that given some particular behavior on the training data points, you can have classifiers with wildly different behaviors in the neighborhood. One does not specify the other. And these are independent quantities.
I see.
Right. Yeah. So the second point there was about the occlusion method assuming that objects were convex and connected, and you can't detect two dots, for instance. And basically, this is the problem that interpretable model classes in literature are often far too simple. That is, they all assume linear interpretable model class, and in particular, these methods cannot capture complex interactions between features. Right. So, for instance, if the model class was a little bit more complicated, you could capture, let's say, multiplicative interactions between features, for instance, which is not possible with the linear model class. And finally, we have this problem that, what if the gray square triggers something else? What if, it triggers a television or whatever? And basically, this kind of hints to the fact that you can't select the neighborhood before knowing what the problem is, right? Or basically, you can't select the counterfactuals before knowing what the problem is. And essentially, searching for the best feature attribution method without knowing anything is basically a fallacy. And we show a little bit of that in the no free lunch theorem, but then, finding out what good neighborhoods are and so on, that needs to be thought about in a little bit more detail, given the task. So in this, in the rest of the talk, I won't focus on pitfall 2 and 3. I'll only focus on pitfall number 1 in more detail. Right. And you can ask, what's the problem with interpreting black box models, right? The problem is essentially that it turns out that this enables us to, quote unquote, fool these explanation methods on black box models. So there are, if you just Google, adversarial manipulation of neural network interpretations or something, you'll get like thousands of papers in this area. And all of them basically use the same exact fact, that the model behavior in the neighborhood and model behavior at training points can be arbitrarily different from each other. And essentially, you can fool, quote unquote, explanation methods by training alternate classifiers with different behavior in the neighborhoods. Right, so this is the problem with interpreting black box models. Although in literature, this is kind of viewed as the fact that current explanation methods are unreliable. I think the correct way to look at it is that it's a categorical error to use these methods to interpret black box models with well-defined behavior. Right. All right. So basically, we have some idea that none of these methods should work, and what are we even doing here? But then I'll discuss some evidence of why this might even work in the first place, right? And this is one paper which we published in ICLR 2021 called Rethinking the Role of Gradient-Based Attribution Methods for Model Interpretability, right? So before this, we actually published another paper on a saliency method called FullGrad. The idea was, you take any classifier and it gives you like a heat map showing, where the classifier is looking at. And we found it to work remarkably well. which was great to us at the time of publishing. But then afterwards, we started thinking, why is this even working that well? Because we never trained the ImageNet classifier to perform, some kind of semantic segmentation, right? So what's actually causing the gradients to have this highly structured nature, right? The common kind of justification for this is that it's the generalization capabilities of the models that lead to this, right? It's because, of course, to recognize the snake or the dog, it needs to look somewhere, and the gradients are telling us exactly that. And this is why these methods work. But then in this talk, I'll show that this is not really true. And in particular, gradients are basically arbitrary. And even in more particular, I'll talk about something called the logic gradients and not the output gradients, right? So many of these methods, including full grad, grad cam, and input gradients, and so on, they basically compute the gradients of the pre-softmax logit over the inputs. And it turns out that these have far less structure than even the softmax gradients. So just to recall the expression of softmax, it's just x of the logits divided by sum of all the logits, where f is the logits and xsi is the softmax for the ith class. And we know from the properties of softmax that it's shift invariant. That is, I can add any arbitrary scalar to all of the logits equally, and then that doesn't change the softmax output. And in particular, instead of adding a scalar, I'll add a scalar valued function, right? Which is no difference, essentially. Basically, G is a function which always returns a scalar in this case, which means that I can replace all the logits f by f tilde, by being f tilde being f plus g, which means that the gradients of the logits are gradient of f plus gradient of g. But then remember, g was an arbitrary function. It has no structure to it, which means that the gradient of f should be arbitrary, right? So this is like a very simple demonstration to show that the logic gradients can be any arbitrary kind of quantity, and it really doesn't impact the softmax outputs essentially, right? But then it turns out somehow majority of salience maps in literature, including the full grad that had this very clean semantic segmentation structure, including grad cam, including smooth grad, including input gradients, for instance, all of these papers talk about logic gradients in particular. And for good reason. If you look at softmax gradients, they tend to produce less sharper visualizations than logic gradients. The question is, what's happening here? If not model generalization, if not the structure of the softmax, what is it that causes gradient structure, right? Okay, so to understand this in a little bit more detail, let's look at this other paper published by Grathwohl et al. Called "Your Classifier is Secretly an Energy-Based Model and You Should Treat It Like One." That was published in actually 2020. So the idea in this paper is that if you look at the softmax output, which gives us P of y given x, it's written in this manner. This is x for something divided by sum of x. It can be made analogous to the expression of Bayes' rule, which helps us define essentially P of x given y as something proportional to the x of the logit. Basically, the idea here is that if I define P of x given y as something proportional to the x of the logit, then this is consistent with the softmax expression that I used typically, right? And this just arises from Bayes' rule. This is just an interpretation. We haven't basically done anything here. And it's also not a very particularly useful interpretation so far, because to compute P of x given y, we need to compute the denominator, which is the partition function. And it's actually intractable to compute this because you need to integrate over all possible inputs in your space. But then it turns out that if you take the gradients of the log of this probability, it's exactly equal to the logic gradients, right? Basically, the normalizing term kind of cancels out. And this is nice because this is exactly the quantity that's of interest. There's logic gradients. And we were wondering, where does it obtain its structure from, right? And it turns out here that it's actually related to the gradient of log of P of x given y, right? Right, and to drive home this point in a little bit more detail, from the previous thing that we just saw, P of x given y does not determine P of y given x uniquely, right? There can be many different P of x given y that can lead to the same P of y given x. All right. So the hypothesis that we make in this talk is that the reason for the structure of logic gradients and logic gradient-based interpretations is the fact that the gradients of log P of the gradients of the logic gradients that the model actually obtains in practice, that is gradient of log P theta, is actually approximately same as the ground truth logic gradients, which is the gradients of log P data, right? So this is the hypothesis that we go with in this paper. And the way we kind of test this in practice is that we increase this gradient alignment in practice and see if that improves any of the interpretability properties of the gradients. And we decrease this alignment property, and then we see if this decreases any of the interpretability properties of the gradients. Right? Any questions so far with the hypothesis before we move on? Okay. And surprisingly, it turns out that the hypothesis which basically said that log P theta and log P data are kind of related to each other is exactly this generative modeling principle called score matching. Right, so score matching is this generative modeling principle, which is very popular these days, where the idea is to basically minimize the difference between gradients of log P theta and gradients of log P data and find appropriate theta that does this eventually. Although when it was first proposed, it was proposed using a slightly different framework by Apo Haivainen in GMLR 2005, where he proposed simplifying this expression by using terms related to the trace of the Hessian and the gradient norm and so on. And to see a simple reason for why this should be true, first of all, the reason to simplify this is because we don't have access to gradient of log P data, right? We only have samples from P data, but we don't have access to its gradients. So one intuition to see what this expression by Apo Haivainen is doing is that the second term tries to make sure that the density is flat at the data points, right? So for instance, let's assume that we are given a Dirac delta density. We want the density to be flat at the data points, as we see here with the dotted line, which corresponds to the second term. And the first term basically corresponds to these arrows, which tries to kind of shrink the density to be as tall as possible. And that's equivalent to basically minimizing the trace of the Hessian, essentially. Right. But the problem with this original formulation, which is of course not the case anymore with all the large-scale diffusion models that we see today, which also use the same formulation, by the way, is that Hessian computation is actually intractable for deep models, and the trace of the Hessian is actually unbounded below, which basically means that the trace of the Hessian can go to negative infinity if you're not careful, for instance. In other words, the Dirac delta can become, we can basically end up with very spiky Dirac delta distributions after doing score matching, essentially. So in practice, what we end up doing is that we propose efficient ways to estimate this Hessian trace using something called Hutchinson trick, and we propose a way to regularize this. The details here are not very important, but what is important is the fact that score matching doesn't work as it is out of the box, and we need to do some small tweaks to make sure that it's practical and first of all, that it's stable. Right. So coming to the experiments, let me try to do this again. Yeah. What we do here is basically we train models with a regularized loss, which involves training first a cross entropy term and a regularization on the logits, encouraging them to have the generative property, right? Oops. So we don't need to look at what the term exactly is. We talked about it a little bit in the last slide, but basically you can think of that as a term that encourages logits to be aligned to P of X even Y via score matching, right? So to verify our hypothesis, we train 4 models. The first is the baseline standard ResNet model, let's say. The second is the score matched regularized model. So here, the logits are more generative than the baseline using this kind of regularization. We also train an anti-score matching regularizer where the logits are actually less generative than the baseline, right? By just inverting the sign of lambda here. And finally, we just use another baseline, which is just gradient norm regularization, which is just a robust baseline. Although we have more experiments in the paper, the main point here is that on this particular test of goodness of interpretability methods, which is the pixel perturbation test, which we also saw previously, where the idea is to mask out different fractions of the input and see if the classifier still recognizes the image correctly. We see that the more generative models perform better than the less generative models. So for instance, the anti-score matching model performs the worst, and the score matched model performs the best, right? Yeah.
What do you mean by more generative?
So by more generative, I mean models that are trained with score matching regularized score matching regularization on the logits. I just call them more generative as a shorthand.
So it's not just the regularization part versus it just means you're using for, why are you calling them more generative?
Because the regularization here encourages the logits to be aligned to P of X given Y. And the shorthand I use for that is that logits are more generative.
Okay.
So I think we have it online.
Yeah, sure. Go ahead, Anya.
Hi. I have I don't think I completely understand what you were proposing. So the idea was that the structure of gradients is tied to the smoothness of the trace, right? When you have the score matching laws. But then in standard gradient, in contrastive learning based, not contrastive, cross entropy based learning, you don't have an explicit score matching as such.
Mm-hmm.
So I see a disconnect. How do you tie the score matching generative models with cross entropy based learning to see where the gradient structure is coming from?
Yeah, that's a very good point. So we don't know exactly where the generative structure of the logits are coming from. We know that they exist. We know that some structure exists just empirically because of the way the logit gradient maps behave. For instance, we're just trying to see here whether increasing or decreasing the generative structure of the logits actually influences this, right? So, which is why we have this other baseline, which is anti-score matching, which actually reduces the generative capability, which essentially applies the same regularization, but with a negative term, with lambda being negative, essentially. Does that make sense?
I see. Okay. Yeah, we can talk in detail later. Perhaps.
Okay, sure. Thanks. Right. So essentially, this means that if we use regularizers, such as score matching or just robustness-based regularizers, that ends up producing models that whose gradients perform well under this metric. On the other hand, if we have either standard models or anti-score match models whose gradients are deliberately quote unquote corrupted in some sense, then these end up performing worse under this metric, right? Essentially, this kind of confirms our hypothesis, at least in this case, that implicit density modeling influences gradient faithfulness, right? Okay. And more broadly, what this kind of tells us is that the interpretability methods which people have been using in literature might accidentally be related to generative modeling techniques. And so what do we mean by that? So we saw already that logit gradients might be related to the gradient of the log probability, which has to do with generative modeling. But then if we look at things like deep dreams, for instance, or activation maximization, which is a classical way to visualize deep neural networks by just optimizing the inputs to maximize some particular logic or some particular neuron, for instance, that is actually analogous to MCMC sampling via Langevin dynamics over these densities, right? Although it's not exactly the same, these methods are actually equivalent to producing the mode of the density rather than samples from the density, right? So which are exactly these kind of samples that we see here, although I realize they're probably not very visible in the slides. But yeah, so this could be something that explains the behavior of these methods, although they have no reason to exist really. Okay, so the takeaway of this part of the presentation is that we've presented some evidence that logic gradients are related to P of X given Y and not P of Y given X, which they're typically used to interpret. Remember, we wanted to do all this because we wanted to understand the properties of P of Y given X. But then what we're actually doing is that we're actually visualizing things related to P of X given Y. And depending on how we train P of X given Y, we could get any interpretation that we want, right? Which is not great. The broad message here, as with some of the previous discussions we had, is that gradient structure depends on factors outside the discriminative properties of the model. We can't just take a pre-trained model and hope that the gradients are meaningful, right? And a lot of interpretability methods in literature might secretly be generative modeling methods, essentially, right? If you want to play around with some of these methods, the code is available online. Okay, so yeah, maybe I'll pause here a little bit more to see if there are more questions. Or maybe I think I should move on. Yeah. Fortunately, this part will not be very long. The question is, okay, we are kind of in trouble now. Like, how do we, so what's the path ahead? It turns out that one obvious way to kind of overcome these limitations is to train robust models. So remember, the problem was that we didn't know what the neighborhood looked like. So the gradients could be anything we wanted. But then this is kind of avoided when we train robust models. By robust here, I mean models like adversarial robust models in the L2 sense. So as an example, this particular paper by Harsha and colleagues, published in Neuroscience 2021, shows that if you take this very simple data set that discriminates between LMS class 0 and class 1, with the main diagonals being non-informative, then we see that the gradients of standard models actually place attributions on both the informative parts and the non-informative parts, which is not very helpful. But then the gradients of robust models, for instance, do not do this. The gradients of robust models are more discriminative, and they do not place attributions on the non-informative parts. And this is quite encouraging for us. This means that if you actually explicitly train models with well-defined behavior in the neighborhood, we can expect these gradient methods to perform well, right? But then, of course, the problem is that adversarial robustness does not quote unquote work, in the sense that there's always a trade-off between adversarial robustness and performance on the clean samples, right? So question is, can we do anything about this? So one way to kind of go around the problem is to not look at adversarial perturbations at all, but just look at random perturbations, right? And one of the things that we looked at in a previous paper was to do exactly this, but for distillation. But the idea was basically that if you want to produce a model that's robust to random perturbations, then you have to basically evaluate the term on the left, which is actually intractable, because computing this expectation in practice is like very intractable for a large number of dimensions because of the Monte Carlo integration and so on. But then we can approximate this with the Jacobian norm, essentially. And this is a tractable way to get, a robustness to random perturbations. But then, of course, in practice, this doesn't work as well as we would like. So one thing which we thought would help this case was if we had models that were explicitly low curvature, where the gradients were actually informative of perturbations in a larger neighborhood, right? So we'll expand on what we mean by that in a little bit more detail. But in this paper, which we had recently with Kyle, Hema, and Francois, published in Neuroscience 2022, we looked at the problem of training exactly these low curvature neural networks to be able to train robust models more efficiently, right? So the idea here is basically to train models that are as linear as possible. So what do we mean by that? We mean that we want the spectral norm of the second derivative to be small everywhere across the input domain. Right? So this is what we mean by penalizing curvature. And as you can see in this simple DOI example, this produces decision boundaries that are more regular and less chaotic. And this squares well with our overall objective of producing models with well-defined neighborhood properties and not arbitrary neighborhood properties, right? So to go into a little bit more detail about how we could actually do this in practice, there are actually two ways that you could do this in practice. So one is local curvature penalization and the other is global curvature penalization. So when we say local penalization, we mean that we'll just minimize, let's say, the Hessian or the curvature pointwise on the training data, right? So that's what is typically done. But then globally means that I'll minimize an upper bound on curvature across all the data points. So each of these have their own pros and cons. The pros of this is that of local curvature is that this is kind of what we want to do. But then the cons is that the model can still have high curvature outside the training data, right? So we only penalize curvature on the training data, but then if you go a little bit outside, it could still have a high curvature, for instance. And we don't want to have expensive Hessian penalties in practice because nobody's going to want to use them, right? On the other hand, global curvature penalization has exactly the opposite properties. That is, it ensures that the model does not have high curvature anywhere, right? And it's computationally inexpensive in practice. But then the cons are that if the bounds are loose, then we might not do well at curvature penalization at the data points, right? So it's kind of the opposite. But then we'll show that our method actually does not have this con as much as we would think, right? So to go very quickly into what we do in this method, we first define something called as the normalized curvature. For technical reasons, let's just say we just define the normalized curvature as the spectral norm of the Hessian divided by the gradient norm, essentially. And what we end up doing is that we propose an upper bound on this normalized curvature quantity, which essentially tells us that one way to penalize the normalized curvature globally is to actually penalize the spectral norm of all the linear layers that we have in the model, and to penalize the normalized curvature of activation function that we use in the model. This is a very simple layer-wise strategy that this kind of bound proposes. So this is exactly what we do in the paper, essentially. First, we propose a new kind of nonlinearity called centered beta soft plus, which is a more stable variant of the typically used soft plus nonlinearity, which ensures that, okay, so first of all, we use soft plus and center soft plus nonlinearities because it turns out that the beta parameter that we need to input to these nonlinearities is exactly an upper bound on the normalized curvature, which is exactly the quantity that we want to penalize, right? So we want to use beta with soft plus or center soft plus with small beta values. But then if you look at soft plus with small beta values in this red dotted line, it kind of seems to have a high y-intercept. And as this beta gets smaller and smaller, soft plus gets more and more unstable. But then this problem doesn't happen for centered beta soft plus, whose y-intercept stays at 0, regardless of the curvature value. And the point here is to make beta to be a trainable parameter that we can control with regularization, right? And we do the same thing with batch norm, for instance. Turns out it's very difficult to train batch norm to have like a one Lipschitz or a one spectral norm constraint. So we have batch norms. We have batch norms with spectral norm equal to gamma, and make gamma to be a trainable parameter, which we regularize to be as small as possible. Right, but then this problem doesn't occur for convolutional layers, which we can actually explicitly constrain to have a spectral norm equal to 1. Right, so convolutional layers don't give us any kind of sort of problems in this case. And the idea here is to just penalize curvature, to simply penalize beta and gamma. Right, so it's a very simple method. No need to compute any Hessian norms to have this low curvature methods. And optionally, we can also penalize the pointwise gradient norms. Right. And to take a look at the results, our approach is the LCNN and LCNN plus grad reg. We see that we're able to get far lower accuracy without, far lower curvature without compromising accuracy, right? So which is exactly what we wanted to see, because this is a very loose upper bound approach, but then it's interesting that it's able to even penalize pointwise curvature as the training data points, right? And we see that LCNNs improve gradient stability by an order of magnitude, right? So what do we mean by gradient stability? Intuitively, it's just that the relative robustness of these gradients as we move from point X to a point in the neighborhood X plus epsilon, right? So as we move from X to X plus epsilon, gradients stay surprisingly stable for these low curvature models up to an order of magnitude greater, right? And finally, we see that LCNs help in obtaining robustness without degrading accuracy, which was what was our objective to begin with, right? So at least for this very simple case of adversarial robustness, we're able to get comparative accuracies with the canonical adversarial training without losing a lot of accuracy.
So what data set have we discussed?
Oh, sorry, these are all on CPAR 10, CPAR 100. Yeah. So, yeah. Right, so a takeaway of this part of the presentation is that we've developed a simple method to train low curvature neural networks, which basically increase the effectiveness of gradient regularization methods and leads to an order of improvement in magnitude of gradient stability, right? Which is what we care about from the perspective of feature attribution and interpretability. And yes, the code for this is available online as well, and I encourage you to take a look at this. Okay, so as I wrap up the presentation, so far we basically looked at the fact that feature attributions all rely on these gradients or input perturbations, but then black box model may have undefined behavior on these perturbations or gradients, which can lead to these methods being unreliable, right? The current methods may rely on unintended structure that these models already have, introduced by some quote unquote accidental generative modeling or accidental robustness that these may have, but then we should not rely on them. And inductive biases like robustness or having low curvature may help in this case, right? And what does the future look like? If you can allow me a little bit of speculation, is that we shouldn't drop conclusions about model behavior from these attributions, especially if you're using black box models. And I think Cynthia Roden makes the same argument when she says, stop explaining black box machine learning models and use interpretable models instead. Yeah, so the question really here is in point 2 is that we know that robust models are more reliable, but what's the more general use case for them? Like, what's the reason why everybody should be using them beyond feature attribution? Right? So that would make for a very strong use case for using these models. And finally, I think in a lot of the literature on feature attribution and interpretability, we kind of forget our main goal, which is to basically detect spurious correlations and basically characterizing model behavior in realistic settings, which I think we should focus on a lot more going into the future. And with that, I'll conclude my talk. Thank you for your attention and time.
Any questions from the audience?
Okay, just finished like 1 minute.
Matt has a question.
Okay, yeah, sure.
Go ahead, Matt.
Am I audible?
Yes.
Yes.
Okay, good. So you may have actually cut me off with bullet point number 3, but at the beginning of the talk, I was expecting you to say something like the value of an explanation is whatever decision we can make on the basis of that explanation. And now I'm going to go write a formula for the Bayes risk associated with that decision, and and then work my way back to modifications of my model or my learning algorithm. So, but let's just do step 1. What decisions actually hinge upon what you're finding, what you're talking, what you're calling an explanation?
You mean practical modeling decisions? Is that what you're asking?
Yeah, I mean, so it's nice to look at pixels that seem to have, that might cause a lot of variance in the output, but what is the value of an explanation?
Yeah, that's a very good question. So I think one way to look at these explanations is similar to something like we've been using t-SNE, for instance. They're an exploratory tool that helps us, understand, some of the structure of the models that we're training, which we can use to actually, diagnose any spurious correlations, right? So I think the main use case for this is to detect spurious correlations. And I think recently we've seen like growing number of works focusing on this particular task. But yeah, so that would be the more concrete task where these methods are applicable.
Okay. So, I mean, there are other characterizations of these correlations, like just the distance that you need to travel in latent space to get to another classification. So couldn't these be done without regard to the input space?
That is true, but it's often that the input space is more easily, I don't want to say interpretable, but it's just that the intermediate features always can anyway have arbitrary structure, right? In the sense that we have no reason to assume that the intermediate features mean anything. But I agree with your point that if there were intermediate features where we had precise semantic meanings that we could attach to, then we should be doing that. But since we don't have that for a large number of applications, I don't think this is what people usually lean on towards doing.
Okay, thanks.
Thank you.
We have a question from Anu.
Okay.
Yeah, I have actually 2 questions. One is this low curvature stuff that you presented. I'm just trying to understand like how is it impacting the interpretability? Or I didn't see really a visualization of how the interpretability changes with low curvature. What was the insight there? The TNM models are better to interpret, or?
Yeah, so we didn't include any visualizations here, but essentially they kind of follow the same behavior as they do for any of the other robust models. So that's what we found. It's just that they now no longer have the trade-off with clean accuracy that that is classically obtained, right? So we saw some behavior of gradient norm regularized models in the rethinking paper or even some of the earlier slides, but yeah, so qualitatively, I think the gradients are, maybe if I can go back to this particular slide. Yeah, so qualitatively, they are very similar to what we would get with, let's say, adversarially trained models, for instance, in this case. But yeah.
I see. And my second question is, beyond like post hoc explanations, what do you think of like all these inherently interpretable models like proto-p-nets and such? What is your take on those?
Yeah, so I mean, I don't know. I mean, there are a lot of so-called inherently interpretable models, but I don't know if we can get actually, precise insights from these, because inherently interpretable is a very strong statement in my point of view. Yeah, so I think that's what I think these days, because even for things like something like proto-p, for instance, I don't know like what's the level of precision to which we can make the statement that this other image has a peak like this other training image and so on. I think it's useful as a visualization or something, but yeah, again, I think it's getting precise insights where these models kind of miss out is what I think.
Okay, I see. Okay, thanks.
Maybe you can also quickly comment on some of the stuff I've seen about causal invariance from, I think, really on board too, and about variant risk minimization. Those papers sound very nice to me, but do you have any thoughts on?
Yeah, I think
so that the eventual goal that you want to reach.
Yeah, I think if we had a method which did what that paper claimed to do, then that would be great. But then we still need methods to say whether they were successful or not, right? Yeah. But my understanding is that the original method apparently has some drawbacks when applied in practice and so on. So yeah, but I think the core problem remains of that of guarding against Fourier's correlations.
Right? Any other questions?
So have you ever tested proposed method on the speech or audio data set?
So I haven't done this, but at IRIAP, we had some colleagues in the speech recognition department who use some of these methods to apply some insights for speech processing systems. I think it worked to some limited degree there because, again, as with every other model, people use black box models to interpret them, right? And like, I don't really know if the insights that you get from them are going to be reliable or not. So yeah.
But still, I think visual image features are much more complicated. Context is spots, right?
Yeah.
But speech case or audio case, much more clear picture. The context is much more clear.
Yeah.
If you the voice for the context,
yeah.
Yeah.
So I remember, like my colleagues, what they did was they visualized which frequencies were more relevant for some particular classification, for instance, and they used that to kind of determine whether it was working as intended. Apparently, they had this finding that it was similar to what they expected in terms of the human perception, for instance. But yeah, I've only read that work in very briefly.
So maybe I'll ask one last question. What do you think about, everybody's using transformers now for everything, right? And there, you often see people visualizing the attention matrices, right? Like kind of where they're looking and stuff. How does that kind of?
So I think that has exactly the same problem as using gradients, for instance. Right? You can have many different attention maps that all, give rise to the same input-output behavior. And I mean, I don't know if you've probably come across these papers that their attention is not explanation and their attention is not explanation and so on. But I think the main problem remains is that these methods should not work, but in practice they do. And the first paper basically says that attention is not explanation, says that this method should not work. Attention is not explanation, says that they still do in practice, right? The question is, why are these methods working in practice? And we should basically not rely on them, because of some accidental properties. So yeah.